This video is going to continue looking at aldehydes and ketones. Since we introduced Grignard reagents in the last video, I wanted to show you the complexity of them with different functional groups. So even if you haven't heard about esters yet, you can see the similarities and see what you're going to see when we talk about Grignards with a different type of functional group. Grignard reagents and esters are still going to make alcohols, but what they'll do is after a addition of a Grignard reagent, we now have a good leaving group where our methyl ester piece can leave. After this first step, here is where you make a ketone. This reaction, a ketone with a Grignard reagent, we covered in the last video, so it will add again, giving an O- and then adding a H on there through acid workup. So the difference is, depending on the reactivity of the functional group, you might be able to have a Grignard add twice, because instead of having a poor leaving group like C- or H-, which we had in aldehydes and ketones, you can have a better leaving group. These will still end up being tertiary alcohols like we saw with ketones. Let's look at how this mechanism will be different. Your first two arrows, even though it's a different functional group, would be the same. Arrows coming from the bond between carbon and magnesium, attacking the carbon, pushing electrons out onto the oxygen. At this point, you have a tetrahedral intermediate, which can have the oxygen pushed back down and kick out your OCH3 group. What's the incentive for this? Well, what is happier having the negative charge? Just an oxygen or an oxygen with a methyl group? So as that group is kicked out, we now regain our functionality of a ketone, which is why I like to show this with the aldehydes and ketones chapter. This reaction is one you already know, right? Having the same bond coming from the methyl Grignard, kicking out electrons onto the oxygen. At this point, we do not have a good leaving group, meaning that oxygen is going to hold on to that negative charge until acid workup turns it into a tertiary alcohol. Another functional group is called an acyl or an acid chloride. Here, we're going to see the same mechanism that we had with an ester. In this case, two equivalents of the Grignard reagent will be added, one replacing the bond in the carbonyl, one replacing the chlorine. Let's take a second to review what we talked about with aldehydes and ketones before. We had our nucleophile coming in, having our oxygen have the negative charge. At this point, we cannot kick out either R or Z, meaning our oxygen will pick up our hydrogen. So in aldehydes and ketones, we cannot create a good leaving group. We will have nucleophilic addition. Knowing what we talked about with esters, knowing what you now know about esters and from Grignards with ketones and aldehydes, I want you to try to draw this mechanism on your own. This is where seeing similarities with different functional groups can help you think about the chemistry that's happening. Just like with Grignards, we'll see the bond between the carbon and the magnesium act as your nucleophile, pushing into the carbon, pushing electrons out onto the oxygen. At this point, you have another tetrahedral intermediate with 4 groups, and you can decide which group is going to be the happiest with the negative charge. Oxygen here can push down and have chlorine leave. This is something we couldn't do with aldehydes and ketones because H- and C- are not as stable as Cl-. At this point, we can make another ketone, which another equivalent of our Grignard can come in, push electrons out. Since I didn't provide any acid workup, your final answer would be the intermediate with the negative charge on the oxygen. Let's go back to looking at reactions of aldehydes and ketones with a different nucleophile. Here, this is a nitrile or a cyano group. Having this nucleophile is no different from a Grignard, right? This still has a carbon with a negative charge on it. If we react this with acid, acid is there to protonate the carbonyl group. We can have our new CC bond at our carbonyl position. Let's look at this mechanism. Just the same arrows we drew with a Grignard. A nucleophile coming in, electrons going out. Oxygen can then pick up a hydrogen or either from the HCl or the Cn-, and that will be similar to your acid workup step, where you have your OH group and your nitrile group or cyano group next to each other. You can do a couple different things with these groups. When you react this functional group known as a cyanohydrin with acid and water, you actually can replace it to what's known as an alpha hydroxycarboxylic acid. All that means is next door to the carboxylic acid you have an OH or a hydroxy group. You can also use hydrogenation, which is something we saw with alkenes, where you can replace any level of unsaturation with hydrogens. This is known as reduction to a primary amine with an OH group on the beta carbon, and this is just referencing how many carbons are between the OH and the nitrogen. Other reactions that aldehydes and ketones can undergo is with a hydride ion. This is a nucleophile very similar to Grignard. Instead of C-, you're actually creating H-, meaning a new hydrogen is added to the carbonyl position. So with aldehydes, you'll get a primary alcohol. With ketones, you'll have one equivalent adding, making a secondary alcohol. The mechanism for this is very similar to Grignard's, the same arrows we've been drawing coming into the carbonyl, pushing out. Notice where the arrow's starting from, the H between the B and the fourth hydrogen. This allows one hydrogen to add at our carbonyl position. In this case, this is just like with aldehydes. We cannot have an H- or an R' leave, meaning our negative charge is localized or stuck on our oxygen, and acid workup will turn that into a primary or secondary alcohol depending on what your R' is. I want you to think about what would change if we have sodium borohydride with an acid chloride. Do we have the same type of restriction where we can only add one hydrogen? We actually can add two, because instead of having a poor leaving group, Cl- will make a great leaving group. So we can turn an acid chloride into a primary alcohol. This should remind you of, just like with Grignard's, what we saw with esters and other acid chlorides. The mechanism for this would be the same. Your two arrows, again, hopefully you're starting to see some similarities. These should all be the same starting point. At this point, you'd have a tetrahedral intermediate where your O- can push down, kick out your chlorine. You've now made an aldehyde or a ketone, which can then react again with another equivalent of the sodium borohydride. Notice your arrows in the first and third steps are identical. I did not draw the acid workup step here, but that would also be similar if you had to draw that from what we see with Grignard's.